So today we'll finish the black holes part, dynamical horizons. So that's what we started doing last time. And so, in a real sense, dynamical horizons are much richer physical content. Right? That's when dynamical things happen, the full nonlinear regime of general relativity, when the black holes are formed or when the black holes collide. But we're going to spend relatively little time on it, just because the mathematical background that is needed, I think you already have for isolated horizons or for the weakly isolated horizons, non-expanding horizons, which are null. You did not have the mathematical background, so we spent a little more time on this. Okay, so the dynamical horizon, as we saw last time, is just a three-dimensional non-null is what I should say, but I think for definiteness we're saying space-like. And we'll talk about today about what the difference is between space-like and time-like, three-dimensional space-like. Manifold, submanifold. Of our physical space-time. Which is foliated by marginally trapped surfaces. So theta sub L equals 0. But also, so this is the outward future directed null normal, and then the other null normal, which is also future directed inward future directed null normal. The expansion here is strictly negative. And I explained why this is the case. The idea is that typically you have two light fronts. And in this room, in weak field approximation, one of the light fronts is expanding, the other one is contracting. And in this case, this is the boundary case when the light front is frozen and the other one is contracted. So this is, and the future directed, as I told you last time, has to do with the black hole type horizons as opposed to white hole type. Outward has to do with the black hole type horizons versus white hole type horizons. Okay, and then we have this sort of the prototype example of the white gas space-time, which is a collapse of a null fluid. So we got a collapse of a null fluid up here. So we got a sky plus here, sky minus here, and then this line up here is the event horizon, because this is a singularity up here. This is null fluid that is falling in. So this is m of v. Here m dot of v equal to 0. Here m of v equal to 0. So here there is no m of v, just so if this is v1, v2. M of v here is just equal to m of v1, which is fixed once and for all. So m dot is equal to 0. And this is what happens. And then what we saw last time was that the dynamical horizon of interest is this space-like surface which starts forming and then joins on to the isolated horizon up here. This bit up here is going to be isolated horizon. This bit up here is the dynamical horizon, which is growing. The isolated horizon area is fixed. In the past of this space-time, this region up here, space-time is just Minkowski space, and the region up here is Schwarzschild. We've seen it many times, but sometimes it takes a while to get it. So this is the picture that we have. So if you have any questions, please ask about this picture. So this was the dynamical horizon, and the analytic equation of this is that the radius along this along this dynamical horizon. So R of V is just equal to M of V. So R is changing as you know because it's in falling matter, and up here then R becomes constant. So here R is just equal to R is just equal to M of V1. So that is just constant. Okay. So this is the thing that we are trying to model up here. Now the point up here is that what is happening to this area increase, and you know black holes are growing and so on and so forth. So what is happening up here? So the first of all, we would like to show that in fact space-like, this manifold subspace-like implies that the area of this dynamical horizon is always increasing. You remember the area of the isolated horizon was constant, now it is increasing. So why does it follow? Well, what we can do is we're going to have these two null normals. So one of the null normals up to the so I'll draw the dynamical horizon up here separately. So here is the dynamical horizon that is given to us. This is the dynamical horizon. And there are going to be two null normals. Here it sort of ends and becomes space-like, null up here, but let me just continue here just for the sake of symmetric drawing. So supposing you're going to dynamical horizon like that, then the statement is that I'm going to have null normals. So this is this vector up here, I'm going to call RA. Now, if this is a space-like surface, it is going to have a time-like vector. So that time-like normal, and that time-like normal, I'm going to, or R hat if you like, that I'm going to get P hat A up here, tau hat A. And then we got two null directions, and these two null directions are going to be outward pointing. So this is LA, and the other null direction I'm going to call NA. So there are four vectors up here. This is a dynamical horizon, and what we're doing is we're just looking at it is foliated by marginally trapped surfaces. So that this just it doesn't happen. We don't have to care what is happening in the past, so we can just look at a piece of dynamical horizon like that. So it is foliated by marginally trapped surfaces. So it's a 3D-dimensional surface. So this is a marginally trapped surface. So I'm looking at the radial vector, which is tangential to the dynamical horizon. So this vector is tangential to the dynamical horizon and normal to the marginally trapped surfaces. Is this clear? So I got a dynamical horizon. I got these two spheres. These two spheres are all marginally trapped surfaces, and I got a vector within the dynamical horizon, a space-like vector, which is going to be the normal. It is within the dynamical horizon, but normal to the foliation. Is this clear? No? Yes. Ask some questions.
How do we know that is the case?
What is the case?
How do we know that it is the case? Like
what is this?
that it is. Oh, it's normal to the.
No, this is the definition of this vector.
Oh, it is the definition.
Yeah. So I'm just I'm drawing some vectors up here. That one vector is, and I'm saying something trivial. I don't know. I'm not saying it well, so that's why it's puzzling. So I got some space-like vector, space-like manifold here. So this is our dynamical horizon up here, and in the space-like manifold, there's going to be some direction, which is going to be within the three manifold, but is normal to the surface. So in Euclidean space, there's a flat space up here. I got a two sphere, and then I just look at the normal to this two sphere, right? So that's all I'm doing here. This is normal to that surface. But then this is a three-dimensional surface. There's also time-like normal to it. That time-like normal is this tau hat up here. So I think I'm just going to draw these two things here separately, not mix too many things. But now, given these two normals, I also have two null normals that I can construct. So the null normals are all going to be perpendicular to this surface. Therefore, they are going to be linear combination of tau hat and r hat. Because tau hat is normal perpendicular to this surface, and tau hat is perpendicular to the whole dynamical horizon. Therefore, it is also perpendicular to this surface. So the two plane, which is perpendicular to this manifold, is r hat t hat. Is a time-like two plane, which is r hat t hat. Is this clear? People look puzzled. Please ask some questions. I don't know. I'm saying something totally trivial, but obviously I'm not saying it well. So that's why everybody looks a little bit puzzled. I got a 4-dimensional manifold. I got a 2-dimensional marginally trapped surface which lies in a 3-dimensional space-like surface. So I'm going to have one radial vector within the 3-dimensional marginally trapped surface, which is called r hat, which is tangential to the marginally trapped surface but perpendicular to the 2-sphere. I'm going to have a time-like vector which is perpendicular to the 3-dimensional space-like surface. Yes? And that is tau hat. Okay. And now these are two vectors which are perpendicular to the space-like surface. Therefore, I can take their linear combinations and construct null. One is space-like, one is time-like. So I can construct linear combinations so that I'll get two null vectors, one of which is outward pointing and the other one of which is inward pointing. So if you like, tau hat, LA. LA is this vector up here is going to be equal to tau hat A plus r hat A. Usually you put square root of 2, but in the dynamical horizon literature, to avoid factors of square root of 2, one doesn't do that, so one just writes this. It's a null vector, so normalization is up to us, and n hat A, NA is just equal to tau hat A minus r. This is exactly what we did in the Minkowski space, except that we put square root of 2. So because we don't put square root of 2, LA and A is now minus 2, because I get here tau hat times tau hat, that is minus 1, plus and minus, so minus r hat times r hat, there's another minus 1, so I get minus 2. So I'm sorry about this, but this is a literature discrepancy in the normalization, and that's what I'm going to use. So I got these 4 vectors that we're going to consider up here. And now the question is really, what is happening to the expansion of this? See, now we want to know how is the area of this surface changing as we move along the dynamical horizon. So if I move from this surface to this surface, is the area increasing or is it decreasing? That's what we want to consider. So what I would like to know is the change in area here, the rate of change in area. This rate of change in area is always given by just the derivative of the 2-dimensional epsilon two-dimensional area element along r hat A is equal to something times epsilon again, and this is the expansion along r hat A, so this is expansion along r hat A. It is really just the divergence, so this is just equal to, if in fact SAB, if I write SAB as a 2-sphere metric, as we always do, SAB to be equal to GAB minus twice LA NB. Let's see. So if I write here SAB to be this is the 2-sphere metric on 2-sphere. Marginal trap, metrical marginal trap surfaces. So this quantity theta is just given by SAB times grad A of r hat B. If you like, this is just the trace of the extrinsic curvature of this 2-sphere regarded as a submanifold of the 3-dimensional manifold up here. So these are all simple ways of looking at it, and that is what the rate of change of area is up here. So this is what we want to calculate. We want to calculate what is SAB times grad A times r hat B. So this is expansion. And then this is just by definition, right? I just substitute what is r hat. So r hat is equal to 1/2 L minus L minus N. So I get here SAB grad A of LB and NB. I just substitute for r hat is what it was, L minus N. So the first is SAB grad A LB, but SAB grad A LB is just the expansion of L. And SAB grad A NB is expansion of N. But this by definition is 0, and this by definition is negative. And I got a minus sign here, so therefore it follows that this is bigger than 0. Well, if this is bigger than 0, that tells us immediately that the area of marginally trapped surfaces within the dynamical horizon is increasing to future. How do I know it is future? It is because of my conventions. L and N are both future directed vectors. R is really outward pointing normal. So if I go to future by the space-like directions, by taking intersection of the dynamical horizon by space-like surfaces, then I'm moving in the future, and so the area is actually increasing. So it's not a very deep statement, right? I mean, it's just two-line proof that the area of the dynamical horizon always increases. The great Hawking theorem is about the event horizons, which says the area of the event horizon can never decrease. And the statement is that for dynamical horizons, the corresponding statement is almost trivial, if you like, it just follows from the definition of the dynamical horizon. And furthermore, it doesn't really have anything with global things. It's just a local thing that we didn't really do anything global up here. I don't want to say that this theorem is therefore on the same footing as Hawking theorem. Hawking theorem is both, is a very global theorem. It has to do with the event horizons. It's a much deeper theorem than this result up here. But on the other hand, the physical content is again the same, namely the area does not really decrease. But the important thing that is going to happen just now, today, is that in Hawking's result for the event horizon, the area is just is never decreasing. So that's the statement, the area can never decrease up here. But we don't know what the cause of it is. We don't relate it to the flux of matter or flux of energy. We don't say the increase in area is given by some physical process, right? And this is the example that I've repeatedly emphasized about 6 times now, that in the Minkowski space-time up here, the area is increasing, nothing is happening up here. So for event horizon, it is impossible to have a local result which says that the area here increased because something fell into the horizon. Nothing is happening here, it's just flat space-time. But here we'll see, there's a main result today, that in fact, that this growth of area is directly related to the physical processes. In other words, really, it is because things fall into the black hole that the area increases. Now, when I started thinking about it first, I had an immediate roadblock, right? Everybody had this immediate roadblock, that a result like this could possibly not be true. The reason why that can possibly not be true. Because what is your expectation? Your expectation is that I got some horizon, this dynamical horizon, and in this dynamical horizon, things are falling in. And you would imagine that the area increases because the energy that is falling in, is going to be because of the energy that is falling in. Now for matter, it's reasonable to say what that energy should be. I can have stress energy tensor of the matter, but I also need a preferred vector field with respect to whom I'm talking about this energy. So I could take that vector field to be equal to tau, or I could take it to be equal to L, or I could take it to be equal to N. I got some preferred vector fields here, I could put them and say, well, that is giving the measure of energy that is actually falling across this dynamical horizon. But what about gravitational waves? Because obviously gravitational waves also fall in, and that increases the area. Right? But there is no local notion of energy, particularly in a strong field regime, of gravitational waves, right? I mean, because we're at infinity, there's the second part of the course, we'll see that there is a notion, when you go out to Scry, there's a notion of how much energy gravitational waves carry and so on. But locally, we don't have a notion of how much energy gravitational waves are carrying. There's no stress energy tensor for gravitational field, right? So that is the main problem. I mean, you can construct pseudo tensors, but as the notion says, it's pseudo. So it's not really a tensorial object, it depends on your coordinate system. So if you integrate some quantity, then you might get a gauge invariant result. But if you just look at a local quantity, if you just ask me what is the flux of gravitational waves across this table, that has no unambiguous answer. I think this is important for people in gravitational waves, that story has no unambiguous answer. It's really what is happening at infinity that one can actually calculate unambiguously in general relativity. So my obstacle was that, well, I mean, but this is a strong field regime, and the gravitational waves are following it. That should also actually increase the area of the horizon. And how can I ever know? I mean, there's no formula, local formula for the gravitational waves. crossing surface, a space-like surface like that. And so how could it have a formula like that? And I think this is the kind of probably the reason why for the longest time, when people thought about maybe trying to do something in a local way, one did not succeed. But we started thinking anyway with Badrikrishnan, who was a student at that time, and then we found some result which was totally shocking to me. And what happens is that yes, if you give me a random surface in space-time, then there is no gauge invariant notion of how much gravitational waves, how much energy is carried by gravitational waves across that surface. However, if and only if that surface is foliated by marginally trapped surfaces, you have got a gauge invariant notion of how much energy is carried by gravitational waves across that surface. If I take a surface which is I take a surface a little bit outside, in which the expansion is one expansion is positive, the other expansion is negative, I don't have that notion. If I take a little surface inside where both expansions are negative, I don't have a gauge invariant notion. I have a gauge invariant notion only precisely when the surface is foliated by marginally trapped surfaces. I think this is a deep interplay between geometry and physics, which just comes out of this analysis and which was not known before. Okay, so the ultimate final result is that because of this, there really is a formula, a quantitative formula, which tells you how black holes grow. They grow by swallowing energy, and the energy can be energy in matter as well as energy in gravitational waves. So this is a very, very beautiful interplay between geometry and physics, which had remained not known for almost 100 years since the discovery of, 90 years since the discovery of general relativity. But so this is what we're going to do now. So this result was published in 2000 and something. Just 1 second. Let me just write down this result up here. So how black holes grow is what we want to do. Plus Badrikrishnan. But the dynamical horizons are routinely used by numerical simulations now, so it's not, by now it is kind of old result. Badrikrishnan. Yeah, so it's quite old result, 2003 up here. And this is also discussed in the review paper that I mentioned before, also with Badrikrishnan. It is, I had given you sections, so there is in one section, this particular result is mentioned. There are two questions, I think.
Okay, so first of all, I think I kind of see two definitions for the dynamic horizon here in the blackboard. So one definition is it is the stacking of the MTS. And another way I see it is you define the R hat, and I can read the R hat as L minus N divided by 2. So I don't really see why these two, and you also mentioned that the R hat is parallel tangential to the DH. I don't really see why these two kind of definitions really.
No, there's only one definition. This is the definition.
Yeah, but I don't know why is that L minus N divided by 2 is tangential to that.
This is a definition.
Okay.
So this is a definition, and then I'm looking at, yeah, okay. So I've got a foliation by marginally trapped surfaces. So I forget about space-time. I just look at this dynamical horizon. It's a three-dimensional space-like surface. And therefore, I've got a foliation. So I can look at a vector which is normal to that foliation. That normal I'm calling R hat. I should have written down explicitly. Of course, when I say hat, just means this is equal to +1.
So here you define R hat first. But if I already have the MTS, I can find the L and N first. Right?
Okay, good. So what I'm going one way. We can go the other way in a minute.
Yeah.
Let me go one way because otherwise it'll do. Okay. So this is equal to +1. I'm given. So I'm looking at this definition. I don't know what is L and N. That is a problem. I mean, I know that L is outward normal, N is outward normal, and I know that they are going to be perpendicular to the marginally trapped surfaces. Right? That's all. That's what. At the moment, I don't know what is L. I mean, I'm given this, and I'm given these two vectors. I don't know what is R and tau.
But for instant time, should we know all the information for the black hole, and then we have well-defined MTS, and then we have well-defined LNA?
You need a space-time in the neighborhood of these marginally trapped surfaces. So you just need space-time. You don't need to have global information, right? So somehow in this four-dimensional space-time, think of this as 4 dimensions of 3 for a second. Time is running that way, space-like. So in this, I need a 3-dimensional surface which is foliated by marginally trapped surfaces. So this is true, and the theta sub n is negative. That's what I need. So I can just look at anywhere in space-time and see if there is such a surface. There is or there isn't. If there is, then I say that it has a dynamical horizon.
And once you have that surface we have the L and N, right?
Yeah, so I can L and N, right?
Yes.
I don't have, as you said to begin with, I don't have r hat and tau hat, right? But you give me this surface. Of course, it is in this space-time, MGAB. Therefore, I also have r hat, which is a normal to each of these to each of these marginally trapped surfaces within the dynamical horizon. And I got t hat, which is really the time-like normal to the dynamical horizon.
Okay, then my problem becomes...
Just one
yeah,
second.
sure.
I'm answering your question. If I'm not, then please come back. So I got these two things. Now I just say define these objects, L and N. Okay, I'm defining this L and N. Now your question is, well, but why is this L and N the same as this L and N? That is your question. So this L and N, by construction, is a linear combination of normals to the marginally trapped surfaces. Right? Both of them are normals to the marginally trapped surfaces up here. And given the...
Oh, I get your point.
Okay. So, but now since you asked, I have to complete the sentence. But given the two surfaces, it only has two normals, which are null. Okay. So L and N are two of them. Then this is supposed to be outward. How do I know this is outward? Because of this side. How would I know this is inward? This is because of this side. Okay. So you're completely right. I should have been more pedagogical. I should have started with L and N, and then constructed tau hat and r hat by taking the linear combinations of L and hat. I should have written down tau hat A to be equal to 1/2 times L hat A plus N hat A, and r hat A to be equal to 1/2 times L hat A. So there's my hat here. L A minus N. And then I can check that these are normal or something. Pedagogically, that's what I should have done. I was running ahead because now for most of the time we're going to use r hat and tau hat, and therefore I introduced that. Any other questions?
There's just a quick typo. You were thinking of r hat, but you wrote tau hat, so that's -1.
Where is it?
The norm of tau hat.
No, right? Yeah.
Yeah.
Yes.
Yeah, you either, yeah.
Thank you. Thank you very much.
Yeah.
Okay.
Actually, just a small thing. So the area element, so SAB is a 2-3 metric.
Yeah,
Then the area element isn't that supposed to be antisymmetric, right?
it is.
But then you're saying
No,
equal.
I didn't finish. Sorry. This is good. Okay. This is what was confusing.
Okay, all right. That makes sense.
Thank you. Thank you. Please ask me questions because I'm making some silly typos and that should not confuse you. So please ask me questions. Yeah. So I didn't finish it. I wrote SAB and then I wanted to say what is SAB. I didn't know to finish that.
It's epsilon CD though, right?
Epsilon. AB, CD, CD.
Oh, that.
Yeah.
Yeah, just to clarify the last part. Why is R now tangential with that definition of L minus N?
Why is that? Okay. So And that's the reason why I started with R hat and N hat. That's better to start with R hat and N hat. And then say that I start with the definition of R hat and N hat, and then construct L and N, and then these are the two normals, and then, yeah, I can say it, but it takes longer. So this was more efficient to start with R hat.
It's not just something trivial.
Say it again.
It's not something trivial that I should be seeing more.
Yeah, it is. It's not deep, but I think I'll let you finish today black holes, so therefore, these are algebraic things you can figure out. If not, please come and ask me during office hours, and we'll go through it. All right. I don't want to rush. I mean, I don't want to, anything which is sort of really confusing, I definitely want to stop. But small clarifications is better not to do that. Okay, how? So that's the same thing that we have to know. So what do we have here? I mean, you know, physically we got, I thinking of this black hole and so on. Of course, there's no singularity. All I have is space-time in this dumb three-dimensional surface, right? That's all I have. So it's a three-dimensional surface, which is foliated by marginal trap surfaces with this. Of course, it's not so dumb because the three-dimensional submanifolds which are foliated by marginal trap surfaces don't grow on trees. It is rare to find such surfaces, but still, it is just a three surface which is just given to me, right? And that's all I have. And what else do I have? Of course, I have Einstein's equation. That's all I have. I got this surface and Einstein's equation. And how black holes grow is all embedded in there somehow. So I should get it out, right? And this is the beautiful interplay between geometry and physics. So on the one hand, we think that, you know, black holes are growing, black holes colliding, something is happening. Einstein's equations are Einstein's equations. They just tell me, you know, Einstein GAB or 8 pi times TAB. And then we got the surface. And where did you just put things together? So as you, from the first part of relativity course, you probably know that Einstein's equation is split into what is called initial value equations or constraint. And we also have dynamical equations. In case of Maxwell equation, the constraints are like, there are no time derivatives, so the equations are like divergence of E equal to 0 and divergence of B equal to 0, only special derivative. And the dynamical equations are E dot is equal to plus or minus curl B. I'm smiling because I always get confused about the sign. Is plus or minus curl of B, and B dot is equal to plus or minus curl of E, right? I mean, minus or plus curl of E, the other way. So that is the equation that I got up here. It is the same thing here. There are 4 constraint equations, and there are 6 dynamical equations. Now, what we are given here is a space-like surface. So, the H is a space-like surface. And therefore, I'm going to focus just on this initial value equation. 4 initial value equations. So what are these initial value equations? I should get signs right. I mean, I know what the geometrical part of the constraint is, but I'm going to write it so that the right-hand side has the correct sign. So, the first constraint equation just says that the scalar curvature of the 3 metric, so space-like surface, and then we are going to look at the intrinsic metric. This is much simpler. There's an intrinsic metric on that space-like surface, which we'll call QAB. It has signature plus plus plus, and we got extrinsic curvature. Which we call KAB, which is symmetric tensor. Right? This is equal to QAM, QBN, grad M, down at that. It is how the normal to the surface changes as you go along the surface. So it's the projected, the derivative operator projected into the 3 surface. So I got this thing. And then again, even for Einstein's equation, there's a beautiful thing, right? I mean, these equations were known in geometrical, differential geometry has its identity. which relates 4-dimensional space-time curvature to 3-dimensional space-time curvature. So these are called Gauss and Codazzi equations. They were discovered a long time ago about how the 3-dimensional space-time curvature, 3-dimensional curvature and the extrinsic curvature is related to the 4-dimensional metric, the 4-dimensional curvature, which we really embed this 3-dimensional surface in. So I got 4-dimensional space-time, a 3-dimensional surface, 4-dimensional curvature. Some parts of that 4-dimensional curvature determine what happens to the curvature, intrinsic and extrinsic curvature on the 3-dimensional surface. So what are these equations? The first equation is the scalar curvature. So this is a metric Q. So 3-dimensional scalar curvature minus KAB plus K squared. And this is equal to 2 times. Oh, this can't be right. Yeah, sorry. 16, right? Equal to 16 pi. Times Einstein tensor, so the GAB times tau hat A tau hat B. But actually, if you want to have cosmological constant, this may be too complicated, but since it's a trivial equation, let me just put it. I'll put here T bar, and T bar AB is equal to TAB. So if I have cosmological constant, I just move the cosmological constant on the right hand side, think of it as a part of the stress tensor, and call the total thing to be T bar minus 1 upon 8 pi g times lambda times GAB. So if there is no cosmological constant, then T bar is just the matter stress area tensor. And of course, in differential geometry, this is just the Einstein tensor, RAB minus 1/2 R GAB, tau hat tau. So this is the Gauss equation, and then we got Codazzi equation, which just says that that dB times KAB minus K B. This is called the diffeomorphism or vector constraint, and this is given by 8 pi g, 8 pi times T bar BC tau hat C and then Q BPP is done in A. So we're taking the stress area tensor, or the T bar AB if you like, and I'm going to the effective stress area tensor in presence of a cosmological constant. This is the time component, and this is a space-time component, the mixed component. Yeah.
So what is K again? K of K squared?
Okay, sorry. It's a trace of K. It's a trace of K. And same thing, K here, the trace of K. So these are the two equations. Again, this is really, as I was telling you, these are three-dimensional curvature and three-dimensional extrinsic curvature, the derivative operator of the 3 metric, the three-dimensional extrinsic curvature, how these quantities are related to the 4-dimensional. This is just equal to RAB minus 1/2 R GAB. This quantity up here is just equal to that. So how these 3-dimensional quantities are related to the 4-dimensional quantities is what this Gauss-Codazzi equation are telling you. They are constraint equations. So for simplicity, I'm just going to call the right-hand side up here, which is purely geometric, to be C. So C depends only on Q and K, and this I'm going to call CA. That depends on Q and K. It depends on Q because of Q and also the derivative operator. So this quantity is what I mean by C, and then C is equal to this, and CA is equal to the matter. That is what Einstein's equation tells us. As you must have seen in the first part of our relativity course, that if you give me a 3-metric and extrinsic curvature which satisfy this equation, then the structure of Einstein's equations is such that this is the initial data. The 3-metric is like the configuration variable, like the position, if you like, for a particle. Extrinsic curvature is a dot of the 3-metric, so it's like the velocity. And if you give me the position and the velocity of a particle, then you know what the forces are, then you know the dynamical trajectory of the particle. Einstein's equations sort of tell you, if you like, I know what the force is here. So here, the statement is that you give me the initial data, which is the extrinsic curvature, and the three-metric, sometimes called the first and the second fundamental form. The first fundamental form is the intrinsic metric. The second fundamental form is KB. You're given these two things, then you can evolve and obtain the space-time geometry, four-dimensional space-time, solution to the four-dimensional space-time Einstein's equation. So this is what we have. All we have is these equations, and we have got this very special surface, which is foliated by marginally trapped surfaces. So what we want to do is to just use this and nothing more. And that is going to tell us how black holes grow. So what do we do here? So the idea here is that, well, this is equal to this. So we just are going to multiply this n, by this c, by n, often called the lapse function. I've not chosen the lapse function. I'm going to choose it cleverly so that good things happen. So in other words, so n times c is na times ca. And I'm going to integrate it over a portion of the dynamical horizon. So this is delta h, portion of the dynamical horizon, which is enclosed between two marginally trapped surfaces, S1 and S2. Okay. So this is the portion of the dynamical horizon that I'm integrating on. Okay. So I got a piece of the dynamical horizon by S1 and S2, and a three-dimensional surface I would like to integrate on, and this is just going to be given by, obviously this is going to be given by 8 pi g, 8 pi, I put g equal to 1, times 2 times phi bar AB, tau hat A, plus I'm just getting a little confused with the factors of 2, so let me quickly see that. No, that's correct. Yeah. So the way it is done is 16 pi g times this plus, I multiply the second equation by 2, so I get 2 times tau bc tau hat c, so dbc dybc times tau hat c times q dn. Now the whole point about this kind of taking this combination is that if you take n plus n times tau A plus na times plus na, this vector field is your evolution vector field. This is what is giving you the time evolution. So basically the idea up here is that I got this surface, say one surface sigma 1, in our case this sigma 1 by direct h, and you have got another surface sigma 2. In our case we don't have such a surface, that other surface would be, we can have it, but we're not interested in other surface. The other surface will be here, and then the evolution equation is really you're going from this surface to this surface by this vector field TA, and TA is given by n times tau A plus plus A. Okay, so this is the lapse, and the shift. So this is really, this tau A vector field is really used for the lapse and shift up here. It's really used for the evolution, and the component of tau t in the surface is the lapse, is the shift, and the component of t perpendicular to the surface is called the lapse function times the unit normal up here. So this is the evolution that people have in mind. This is just a side remark This is not the main point that we have, but this is a side remark that I want to make.
So these are 4 quantities, right? C and CA.
Right, there are 4 quantities. There's a vector and a scalar. So there's 3 components and a vector. And now the statement is that what this TA we're going to use. Right? What is the preferred vector field we're going to use in these Einstein? Once you give me T, then I know what is N and NA, and I can just go on. So what is T that we're going to use? And there's no obvious answer to this question, but the natural thing to say is that the preferred vector field is L, because theta sub L is identically equal to 0. So let us use for TA this vector field LA. Now this is not very usual, because usually T is time-like, but there's nothing which says that T has to be time. It can be space-like, it can be null, it can be anything. It just has to be transversal to these surfaces. Right? It should not lie with the surface, it should be transversal to the surface. Yeah.
Sorry, I get lost. Where is the definition for N or NA?
L?
N, the capital N.
Capital A. Okay. So this is something that I just use. So this is introduced. You choose some N and NA. For arbitrary choice of N and NA, this equation is true. And this is the equation I want to use. But of course, for it to be useful, I want to choose N and NA in a clever way. And the question is, well, what is that clever way? Well, first I'll notice that N and NA is really the same as choosing some vector field T, because N is a time component of that vector field, and NA is the component into the 3 surfaces of that vector field. So what I have to do is to choose this vector field T. Then I get N and NA, and I get all this identity, and then all I have to use is this identity up here. So what vector field should I use for the constraints, right? What lapse and shift should I use to smear the constraint functions? And the statement up here is that we should really use something along the direction of M. So the idea up here is that choose TA to be equal to some quantity N, which I don't know yet, some times lapse times LA. So this is idea. And this is our choice. Nobody tells you to. I mean, you can use any, and you get this equation, and you can play with it, and you get wealth of information. And in fact, we did that in the paper. We got a lot of information by changing this L. But the most interesting choice is, not very surprisingly, this T is parallel to L, and then this is N. So the question is, what N are we going to use? And we'll see in a minute that a good N to use is just there's a nice choice of this N to use. Let me just tell you what that is now. So I got this dynamical horizon, and it is foliated by marginally trapped surfaces up here. So this is my delta H, this is S2, and this is S1. So each of these S is a topological to sphere, and then each of the surfaces has an area. So, and I'm going to just use the area, which is a geometrical quantity, and I define the area to be equal to 4 pi r squared. So r is a function that I'm introducing, which is called geometrical radius of the 2 sphere. This is just a definition. This is the area of the marginally trapped surfaces. So I got this marginally trapped surface. So this will be R1. Here the value will be R1. Here I will get some R. Here it will be R2. So I get a function R, which is just obtained by looking at the area of the marginally trapped surfaces, which is a natural function to use. And it turns out, as we will see in a minute why, this N that you want to choose is you take the gradient of R, and gradient of R does not require any derivative operator because it's a function, you can use any derivative operator. So you take the gradient of R, and you just take it now. So if you like, this is just equal to GAB, AR, BR. So it turns out that that is a thing that you would like to use. And why is that the case? We'll see in a minute. At the moment, I'm just motivating that, well, it's a possible choice that you choose, and then you'll get an interesting identity up here. So what are we going to do now? We are going to take N and NA coming from this LA, right? So LA, so therefore TA is now going to be equal to N times LA, and LA is given by tau hat A. plus r hat a plus yeah. So n, this n times tau hat a, so that's really the lapse, and then I get here n times r hat a is going to be my shift. N times r hat a is going to be my shift up here with the same n function, and r hat a is going to be the unit radial vector, and that just follows for the fact the expressions I had written down before. R hat, sorry, yeah, I had written down LA is just equal to so we're just going to use this. And now it's a series of simple operations, I mean, that anybody can do, right? I mean, in fact, most of it was done on this blackboard, a long calculation, but we need to do those calculations. And what is the idea? The idea is, now you take this equation, the equation start, take start with start, with this choice of n and n. With this choice of n and na, n is given by that, and na is given by n times r hat a. This choice. And we got this equation up here, and simplify. And you just simplify using the two things. The first is that just as we obtain in the Gauss-Corazzi equation, we could express a four-dimensional curvature in terms of the three-dimensional curvature and extrinsic curvature. So similarly, express the scalar curvature 3D in terms of 2D scale, 2D curvature, extrinsic and intrinsic curvature. That is to say, just do a 2 plus 1 decomposition. In our equation star, we just use 2 plus 1 decomposition to simplify this r, k, etc., etc. And what I'm going to do is, I'm going to use the two-dimensional quantities. I'm going to put a tilde. So I get r tilde, I will get k tilde, etc. So this r tilde is going to be the scalar curvature of just the two-dimensional surface here, the two-dimensional surface here, the two-dimensional surface here, and k tilde AB is the extrinsic curvature of this two-dimensional surface in the three-dimensional surface. So what we did here was to carry out a 3 plus decomposition of Einstein's equation. That's what we did up here. And now what we're doing is we're looking at the extrinsic, looking at these constraint equations, the extrinsic curvature and the scalar curvature, and carrying out a 2 plus 1 decomposition. It's the same mathematical steps. I mean, I'm not going to go through them, but I just say that we'll carry that out. And the second thing, of course, is use this theta sub L equals 0 everywhere, right? So what does this tell us? This is going to tell us that if I take the SAB times grad A and B equal to 0 everywhere, but SAB grad A LB is just grad A of tau B plus grad A of r hat B, that is equal to 0 everywhere. But this grad A of tau B, when I'm projecting everything into the 3 surface, and S is in particular projecting everything into the 3 surface, this is just the extrinsic curvature K that we talked about. So this is saying that the extrinsic curvature, three-dimensional extrinsic curvature we have, that's what this quantity is. This times SAB, the two-sphere quantity, plus the two-dimensional extrinsic curvature, sorry, two-dimensional metric times this quantity up here. This is just the two-dimensional normal within the 3 surface to the two-dimensional surface S up here. So this is just the trace of the extrinsic curvature, SAB times K tilde AB. So this quantity, if you like, is precisely the two-dimensional metric is the three-dimensional metric. The three-dimensional metric QAB is the two-dimensional metric plus the radial vector. Right? The three-dimensional metric here is two-dimensional metric plus the radial vector. Therefore, SAB KAB is just given by two-dimensional. Two-dimensional SAB is given by three-dimensional metric minus RARB. So I'll just get here trace of the extrinsic curvature that was featuring up here minus R hat A, R hat B times KAB. And then I get here plus K tilde equals. So you don't have very much to play with. All we had to play with, these are just differential geometric equations which convert three-dimensional quantities into the two-dimensional quantities with tilde, and then you are still left with some three-dimensional quantities up here. To me, the great surprise was that when you do the simplification, final result is very neat in the sense that you obtain terms, each of which has a very nice interpretation. So I take this star and I just subtract, I just substitute, and then I obtain the following equation. The equation I obtain is just the following. So then the equation you obtain is that integral on delta H is equal to of the n that we got up here times the two-dimensional scalar curvature times d3b minus 16 pi g times delta H times d bar AB times the vector field TA that I wrote there times B 3B. This is good because this is just saying, so this TA is just equal to n times L. So this is good because this is just saying that this is the flux of energy with respect to this vector field n times NA across the horizon. So that is a very nice interpretation. Then plus I get here delta H times n times sigma of L whole squared plus a certain quantity zeta. So what is zeta? Zeta is a vector field. It has interpretation. It has something with the angular momentum. At the moment, that's not. We don't have to worry about what the interpretation is. So zeta A is just equal to two-dimensional metric Q tilde AB, or what I call SAB, times RHC. Now, so that's the equation you get. So the equation, the star equation, this is if you like star, which is the same equation as star, just simplified, right? Using two things, 2 plus 1 decomposition, and use the fact that theta sub L is equal to 0, and therefore there's a relation between the two-dimensional extrinsic curvature and the three-dimensional extrinsic curvature. And as we saw before, theta sub this is really theta sub L is a relation between the two-dimensional extrinsic curvature and the three-dimensional extrinsic curvature. This equation is just theta sub L is equal to 0. But the interesting thing is that all these complicated terms I had up here, they simplify. The geometrical part just becomes the shear of L whole squared plus d zeta squared. That's all the geometrical part. Now, why is this of interest? Well, right hand side is already, so this is equal to. So right hand side here is already telling you that this is the flux of matter energy with respect to this particular vector field. But this vector field is natural one. And this equation, by the way, is true for any choice of n. I told you that I want to choose this n, but at the moment I can just choose any choice of n. And this equation is just true up here. And we're going to choose this n to be this in order to cause a drastic simplification up here. So this you can think of as being the matter energy falling into the horizon. What about this? Now the point up here is that these I'll just explain it next time, it's 2-line, but so this 3-dimensional volume element can be written as 2-dimensional volume element divided by square and the gradient of R. Just 1 second and ask me a question. So this can be written as 3-dimensional volume element becomes 2-dimensional volume element times dr. So what I'm doing is I'm using R, the capital R, the area radius, as my radial coordinate, and I'm just writing the 3-dimensional volume element in terms of that radial coordinate and this, and then I get here n times R. Okay. And the only skill here was, of course, that's what we did. We just kept n arbitrary. We got this equation, and then we noticed that if I choose n to be equal to dr, then these terms cancel out. If I choose n to be equal to something else, I still get interesting identities, which we have them use. But this is the most interesting of identities. Why? Because now I get here r tilde times dv times dr, and I can write this equation now as just dr, r going from r1 to r2. This was on S1, I got R1, on S2, I got R2. So we're going from R1 to R2 times integral of d2v times the scalar curvature. This is at every value of R, right? This is the integral on 2 sphere of the scalar curvature. And the reason why this is interesting is because this is a topological invariant. Scalar curvature on a compact 2 manifold times R times d2v, this is a Gaussian invariant. So this is in fact exactly equal to 8 pi for a 2 sphere, 0 for a torus is equal to 6, multiple of 8 pi, higher multiples of 8 pi for a higher genus surfaces up here. So for a 2 sphere it is just equal to 8 pi, and therefore I get the equation up here that I get here 8 pi times is a constant, so that comes out. So therefore this just comes out, so I just get here R2 minus R1 times 8 pi. So I put G here, and in the equations I had put G equal to 1, so let me just remove that G up here. So therefore I get here R2 minus R1 times 8 pi is 16 pi of this times this. Therefore I just divide everything by 16 pi, and I will get here R2 minus R1 upon 2 is equal to the stress area tensor times dA of head B d2v d3v. So this is the matter energy flux plus n times sigma squared plus sigma squared. So the growth in the horizon area, R2 is a horizon radius at this time. So the horizon grew from a radius R1 to R2 because matter fell into it, carrying this much amount of energy, and then there is a geometrical term. So obviously, we would like to interpret this geometrical term as a flux of gravitational waves. So this is the gravitational wave energy. And the important thing is that I never in my life thought that I'm going to get a positive definite term. But you get a positive definite term, so it really is something that you can think of as being energy, gravitational wave energy carried by gravitational waves. And now normally you think of this sigma, in perturbation theory and so on, for curve perturbation theory. In fact, you'll get the same formula, but you'll not get zeta, you just get sigma squared if I just did a second order perturbation theory. And we get sigma squared, which is very nice. But you also get this zeta, and this zeta, if you like, is a contribution that you'll not see to second order in perturbation theory. It's a higher order quantity. If it is a curve horizon and do perturbation theory, this quantity just vanishes. In other words, if I take this and think of the dynamical horizon as being a perturbed curve horizon, then I get what we would expect to be the curve space-time solution. So this quantity has all these beautiful properties. It is positive definite, which is something that very rarely happens in the strong curvature region, that you will get some quantity which will be naturally positive definite. That if I did a perturbation theory around curved space-time, I would actually get the answer I expect. And finally, one might say, well, I get this, that's okay, but in this calculation, let me not suppose that theta sub L was 0. Let me not suppose that this is equal to 0. Let me think that it is a small positive and negative quantity. If it's a positive quantity, I'm a little bit outside. If it's a negative quantity, I'm a little bit inside. Then what happens here? Immediately you acquire extra terms, and they are not of the same sign. And therefore, if you give me a random three-dimensional surface, the Gauss-Krawasi equation, Einstein's equation, you can do this foliation, but there is no obvious interpretation of flux of gravitational energy flowing across. You get the interpretation precisely when this surface is foliated by marginal surfaces, theta sub L. So this is how black hole grow. Black hole grows from radius R1 to radius R2 because there is a flux of matter energy in it and there is a flux of gravitational waves energy. This is how the black hole grows. So we're just finished. We have one more minute. So let me summarize this. Namely, dynamical horizons, again, the definition looks extremely simple. It is a quasi-local definition. In this room, there is no dynamical horizon. We know that. Furthermore, in numerical simulations, people actually find these marginally trapped surfaces, and they find the evolution of these marginally trapped surfaces. So, as the simulation goes, they build these dynamical horizons. There are mathematical results due to geometric analysis experts, particularly by Anderson and Mark Mars and Larry Anderson, and Walter Simon, which show that, in fact, if you have if a little marginally trapped surface like this forms, and if certain other stability conditions hold, then in fact the dynamical horizon will actually grow. There are results that geometric analysts by name Greg Galloway and I have proved, which tells you about uniqueness of dynamical horizons. This subject is not closed. People are still working on it, on existence and uniqueness, but already there are quite good results on existence and uniqueness. It is hard because it is in the strong field regime of general relativity. Really, when the two black holes merge, what is happening up here? So we've got these dynamical horizons, but we have this law, which to me is very interesting because A, it is a quantitative law. It is not like the law for the event horizon, which says the area of the event horizon grows. I don't know by how much. I don't know what the cause is. Here, we know what the cause is. If there is no matter density, if there is no gravitational waves, then in fact this will not grow. Then I get isolated horizon. Okay? This happens only because things actually fall into the black hole, and this to me is an extremely beautiful example of an interplay between geometry and physics. Okay, we stop here.